Students, let us go to next topic. Ionic bonds. What is ionic bond? Ionic bond. The definition is it is it is an electrostatic attraction of opposite ions. So one of the chemical bond, and it is electrostatic attraction of opposite ions. Okay. Or it is called electrostatic bond. This is also called electrovalent bond. Electrovalent bond. Because it's an attraction between electrostatic. Okay. Example, sodium chloride, magnesium chloride, calcium oxide, Fe2O3, zinc sulfate, etc. etc. How do you identify a bond between two atoms are ionic or covalent or metallic? That's very important question. Okay, identification of bonds. That's also very important. Okay. Therefore, normally students tell that sodium chloride is an ionic bond. But not only the sodium chloride. I will tell you how to identify different types of bonds. Chemical bonds identification. Chemical bonds identification logic. Identification logic. What is that logic? It's a simple logic. We have covalent, we have ionic, and we have metallic. In the case of covalent, I tell you a lot of example. H2, Cl2, HCl, O2, H2O, carbon dioxide, NO2, NO3, SO3, S8, etc. And a lot of examples: sodium chloride, sodium oxide, potassium sulfate, or zinc sulfide, chromium oxide, iron oxide, copper sulfide, titanium oxide, cesium chloride, etc. Metallic is alloys, metals: sodium, potassium, zinc, tin, lead, titanium, chromium, manganese. Okay. What is this? Manganese. I tell you, a piece of manganese, a piece of aluminium, gold. Students, the gold ornament you wear, silver ornament you wear, a iron bridge where iron atoms are joined together by a metallic bond. Okay. A copper utensil, a platinum ring. Okay. Where in platinum ring, platinum atoms are joined together by metallic bonds. Therefore, now I think you got the idea. Covalent bond, here hydrogen, oxygen, chlorine, hydrogen and oxygen, hydrogen and chlorine, carbon between carbon, that is graphite, diamond, nitrogen and oxygen, carbon and oxygen, sulfur and oxygen. Okay. Therefore, covalent bond is between non-metal atoms. You should know the idea of the non-metal atoms. Metallic bond is between metal atoms. Now you classify here. These left sides are metal. Right sides are non-metal. Therefore, ionic bond is generally between metal and non-metal. This is non-metal interaction. non-metal interaction. This is metal non-metal interaction. This is metal metal interaction. Fine? Fine? Yes. Now our ionic bond is electrostatic force of attraction between opposite charge ions. Between opposite charge ions. Okay. Where the role of opposite charge was taken by metal and non-metals. Metal atoms are positively charged. Okay. Now let us continue the ionic bond. In ionic bond, metal atoms are positive ion or cation. Non-metal atoms are negative ion or anions, negative ion. And their electrostatic force of attraction are called ionic bond. Okay. Now let us go to factors favoring ionic bond formation. 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 Factors favoring. Okay, in the case of factors favor cations and factors favor anions. Factors favor anions. We can generally this. Okay. In the case of factors favoring anions, its ionization energy shall be less. Charge shall be small charge. Okay, size shall be higher. It should have lower ionization energy. It should have a larger size. It should have a lower what I'm telling you, lower size. Higher size, lower charge, lower ionization. For example, cesium plus has better ionic character than rubidium plus, than potassium plus, than Na plus, than K plus. Sorry, Li plus. Similarly, lithium plus has good ionic character than beryllium plus, 2 plus. In the case of factors affecting anion, it should have a high electron gain enthalpy. High electron gain enthalpy. It should have smaller charge. Its size should be smaller. Size shall be smaller. I will tell you some examples. That is, F minus has good ionic character than Cl minus, good ionic character than Br minus, good ionic character than I minus. Okay, F minus has good ionic character than O2 minus, because charge should be smaller, size should be smaller, high electron gain enthalpy. It should have high electron gain. Therefore, these are the factors which favor the ionic bond. There is separate factors for cation formation and anion formation. Okay? Yes. This red is not good, I think. Okay, sorry. That's for in the case of ionic um, bond factors affecting ionic uh, bond formation. Now we will go to another topic. Uh, okay, red is dangerous, I think. Okay, okay, okay. Now, lattice energy. Lattice energy. How sodium chloride molecule exists? That's very, very important question. How sodium chloride exists? How is sodium? Could you get, my question, can you get one sodium chloride molecule like one water molecule? Did you get my question? Can you get one sodium chloride molecule like one water molecule? Never. Never. Because sodium chloride has a different identity, different entity when you compare with water molecules. Because ionic solids have ionic substances or solids have lattices. Lattice. What is lattice? Lattice is the three-dimensional arrangement of opposite ions. Okay. Therefore, ionic solids exist as a lattice. They are three-dimensional arrangement of opposite ions. Fine. That's how lattice, 3D arrangement of opposite ions. Now, lattice energy. Okay. What is the lattice energy? We are going to calculate the lattice energy. Okay. Lattice energy. Can you see the board? Okay, no problem. Lattice energy, it is the amount of energy required to break lattice is a three-dimensional arrangement. Lattice of 1 mole of opposite ions. That is 1 mole Na plus, 1 mole Cl minus are arranged three-dimensionally. That is called a lattice. Have you seen the lattice replica anywhere? No. I will tell you. You go to the bakery where laddu are arranged. That's one kind of lattice. Arrangement of laddus in the bakery are one kind of lattice. Imagine two types of laddu, yellow laddu and red laddu. Yellow laddu is sodium, red laddu is chlorine. Two laddus are in two boxes. You take one each and arrange them in alternate way. Suppose your both boxes containing 1 mole of laddus, then after the arrangement you will get a structure. That structure is the lattice. Now you are going to break that lattice. That is, you are going to separate each laddu into gaseous state. Imagine they are flying away. For that, you should supply the energy. You are going to supply the energy to separate the ladus into gaseous ladus. That is called the lattice energy. Okay, lattice energy is calculated by the equation. Lattice energy is calculated by the equation. Okay. Now lattice energy is equal to U is directly proportional to Z plus Z minus divided by R plus R minus plus, okay, this is, that is Z plus is charge of cation, Z minus is charge of anion, R plus is radius of cation here into radius of cation. This is R minus radius of anion. Therefore, when radius increases, lattice energy decreases. When charge increases, lattice energy increases. Okay. Now let us go to next to Born-Haber cycle or calculation of lattice energy. Born-Haber cycle or calculation of lattice energy. Okay. Born-Haber cycle. Born-Haber cycle. It's a calculation of lattice energy. Born-Haber cycle is used to calculate the lattice energy because we can't determine the lattice energies directly. This is based on Hess's law. Based on Hess's law. Hess's law. We will discuss Hess's law in detail at thermodynamics. Okay. This is explained. Consider formation of sodium chloride. Consider formation of sodium chloride crystal. Imagine you take 1 mole sodium in solid state, 1 mole chlorine, half mole chlorine in gaseous state, and you are getting sodium chloride crystal. The energy, this is called enthalpy of formation, delta H0 formation of sodium. The energy change is called the enthalpy of formation of sodium chloride. That is, you take 1 mole of sodium, half mole of chlorine gas, and let them react. You will get 1 mole of sodium chloride lattice, and the enthalpy change is called the enthalpy of reaction. But you do it in a stepwise manner. That is, you take first sodium solid. First, what you are going to do? You make it a sodium gas. This process is called enthalpy of atomization. Enthalpy of atomization or sublimation. Enthalpy of sublimation or atomization, both are correct. Now you are going to change sodium gas into sodium plus ion. This is called the enthalpy of ionization energy of sodium. Okay. That's all in the case of sodium. Now, this is step 1 or step 2. Now you go into take your chlorine gas, 1 mole chlorine gas into, or half mole chlorine gas into, 1 mole chlorine gas, 2Cl. This is called the enthalpy of dissociation. Enthalpy of dissociation. Okay. Now, you want the only, if you take half mole, therefore you will get to 1 mole, then this will be half enthalpy of dissociation. Okay, because you are taking only for half mole. Now the chlorine react with one electron, gas, this is gas, and you are getting chlorine gas. This is called enthalpy of electron gain enthalpy. Electron gain enthalpy. Therefore, this is the third step. This is the fourth step. Now, in the fifth step, you take your Na plus gas from here and Cl minus gas from here, and join them. Both are 1 mole. You are getting sodium chloride crystal, solid. This is called a lattice energy. Lattice energy or enthalpy of lattice. Now you got all sodium chloride finally. Now in this step, all these 5 processes happened together. In this step you did nothing. You mix sodium solid, you mix half mole of chlorine gas, you got the sodium chloride, heat is released. That is enthalpy of formation of sodium chloride. But later you did all this stepwise. That is, therefore, enthalpy of formation of sodium chloride must be equal to, that is, enthalpy of sublimation. All are standard state, therefore, enthalpy of sublimation plus enthalpy of ionization energy of sodium, because in the standard state, plus the enthalpy of half of the enthalpy of dissociation of chlorine gas, plus electron gain and standard electron gain enthalpy of chlorine, plus lattice energy. This is SS law. If you know all these values, you can calculate the lattice energy. Okay, because this is already known, this is known, this is known, this is known. Therefore, lattice energy can be calculated. Therefore, Born-Haber cycle is used to determine the lattice energy. Okay, this is a Born-Haber cycle. Enthalpy of formation of a solid is equal to enthalpy of sublimation of enthalpy of formation of a crystal is equal to enthalpy of sublimation of that solid plus ionization energy of that solid plus half of the dissociation energy of non-metal plus an electron gain enthalpy of non-metal plus lattice energy. Okay, that's all this topic. Thank you for watching.